Welcome everyone to this week's SETI Institute seminar. Today, I'm very fortunate to have Michele Bannister as our speaker. Michele did her undergraduate work in Christchurch in New Zealand, then went to ANU in Canberra for her PhD, observational astronomy. She's just finishing up a postdoc at U Victoria in British Columbia, and in a couple of months will be starting over at Queen's University in Belfast as research scientist, working primarily on surveys of objects in the outer solar system, which is what she'll be talking about today.
Thank you very much, Michael. So today I'd like to tell you a little bit about the efforts that are underway with researchers centered in Victoria, in Canada, in Taiwan, and here in the United States, as well as across Europe, in a collaboration who are working to understand the structure of the outer solar system. I'm going to spend a little bit of time on the discoveries that we've made to date, and also how we're being able to use this discovery sample and the way in which we're discovering them to constrain the history of our own solar system. And then at the end, I'm going to touch a little on some ongoing work we have to look at the physical properties of these objects, what there is on the surface of them. The thing we're really trying to find out by studying the worlds of the outer solar system is the history of our own solar system backyard. How did the solar system come to be the way that we see it today? The ice giant planets, Uranus and Neptune, that you see here in beautiful crescents, seen by one of our spacecraft some years ago now, have sculpted the orbits and the current locations in space of these small worlds in the outer solar system. There's hundreds of thousands of them left there today, but they're just a fraction of what was originally present. And the way in which we can look at the outer solar system to reconstruct this history, this migration that has taken place of these big ice giants, is we find what is there today, and then we numerically simulate how the migration of these ice giants could have led to the solar system as we see it today. And the way we can do that is with simulations like this one by Rodney Gomez. So here we have the solar system seen in orbital parameter space. So across here, we have the semi-major axis of the shape of the orbit. So there's the size of that, the eccentricity of the orbit, how much it's distorted from being a perfect circle, and the inclination of the orbit, how much it's tilted with respect to the plane of the solar system. And you can see here this kind of green band, this set of little dots. This is, at the start of the simulation, many hundreds, if not thousands, of test particles, of little objects where you're not worrying too much about what mass they are, but they're traces of what's happening, how they're being dynamically moved as giant planets move in their migration. This is the great discovery of the last decade or so of outer solar system work. The solar system as we see it today is not the way that it formed. So when I run this, you'll see at the top there, t equals 0.0 million years. We're going to run this forward with the giant planets influencing their gravity over time. The initial quiet disk is completely disrupted by planetary migration. The green dots, the particles are scattered up, they're moved out, and as Neptune moves outward, you end up shoving a whole bunch of particles into this very dynamically excited state. And you end up with a solar system where, if I just pause it a little, you've lost a large amount of material. So the present solar system is but a shadow of its former self. It's a remnant fraction of the initial amount of mass, several Earth masses indeed, of material that was in this planetesimal disk. And you also end up with objects being located very particularly in orbital parameter space. You end up with different populations as a result. Some of them will be where these blue lines are here, in resonances with Neptune, mean motion resonances. And this just means when Neptune goes around the sun an integer number of times, they also go around the sun an integer number of times. You have the 2-to-1 resonance, the 3-to-2 resonance, and many, many higher order resonances. Because not having more giant planets out beyond here means you can get a filigree of resonance structure where Neptune is dominating what's captured into these little spaces of parameter space. There are actually more kind of funnels on this than lines, but it's a filigree. It's really quite detailed. So the takeaway from what happens as a result of this migration is most of the objects are gone. A few of them are left in these, captured into these resonances. But resonances occupy a very small amount of the available parameter space. They're tiny. And yet today, we see quite a large number of objects captured into these. This is one of the big signatures that something has taken place to change the structure from how it formed to how we see it today. It's really hard to end up in this resonance unless you are pushed around by the gravitational movement of a giant planet. If we now move to have a look top down on the solar system, so going out here, our part of the solar system is right close in, 20 AU. Further out in astronomical units, 20, 40, 60 astronomical units, you can see there Uranus and Neptune, the ice giant planets I was referring to earlier. And you can also see the grey dots of a particular population. Now, this is a model of the population. There are many hundreds of thousands of objects in this particular population. And this is one subpopulation, one resonant population of these ones I was telling you about. This is what are known as the Plutinos, because Pluto is one of these objects. And they occupy the 3-to-2 resonance with Neptune. To understand how we can find these signatures of past migration, there's a number of things that have to come into play in terms of where you look on the sky, where they're distributed around the solar system, and how orbital dynamics forces them to be grouped on the sky as we see them from Earth. So, Pluto and Neptune over here, this is kind of where the galactic plane sits on the sky at the moment. So this is an area where it's very hard to detect these objects because there are many dense stars and a small moving dot moving by lots and lots of stars is normally on top of a star. So things here are kind of hard to find. So, okay, you can see that's probably a place where you don't want to look to find these kinds of objects. But these numbers around here are hours of right ascension, hours of where you look on the sky to see these things at zenith at different times of the year. And if I show you what happens if I was to take a large aperture telescope, like the Canada-France-Hawaii telescope, which is one of the ones I use most, and apply the fact that its mirror, 4 meters in diameter, can only see objects that are so faint, down to a particular magnitude, that flux limit is what this does to what's observable about this population. The ones up to the left and down to the right there are gone in that perspective. They're simply not visible to the telescope. And a 4-meter telescope, a 4-meter optical telescope, is a pretty big telescope. It's still one of the biggest telescopes in the world that you can use for this kind of search. This is just one way in which the discovery of objects in the outer solar system can have a bias introduced on it. That's a flux bias. Another one is going to be a pointing bias. If I look over here, which this time of year, 14 to 16 hours, this would be discovery of objects in April through about May, I will see a denser region of this population than if I was to come over here around 22 hours to 0 hours and look in the middle of Northern Hemisphere summer. So when you choose to look at the sky, at the part of the sky that's most observable for most of the night, determines which objects you find. Then there's really insidious biases. There's ephemeris or tracking bias. When you find a solar system distant object, it moves across the sky at a particular rate that tells you that it's very distant in the solar system. But if you make an assumption about what orbit it's on in the outer solar system and then change where you next look at it to find it again, that is an assumption that you are making about what type of orbits it's on. This is a subtle bias, it's a tricky bias, and it's only really overcome by looking at these objects very frequently to confirm that your initial assumption about what sort of an orbit it's on is actually valid. At the worst, it can mean that you lose objects. There are, at the moment, of the 1,900 objects that are listed in the Minor Planet Center, which is the clearinghouse reservoir for where objects discovered all around the world are kept. It's the International Astronomical Union's master list of what we know about the solar system. There's 1,900. Barely 1,000 are objects where you can say that we know their orbits with any certainty. 16% of these objects are orbits that are effectively endangered. 17% are objects that are lost. I could not point a telescope at them. We know once that somebody saw them, but we have no idea where they now are. These are the effects of ephemeris bias. And finally, you have detection bias, which is the software that you use to extract moving objects from the data. How good is that at finding objects? And the way you can test that is by planting synthetic objects into your images and running your detection pipeline and testing how well it recovers them. That's more quantifiable. But the terrible amount of ephemeris tracking bias that you have means that if you're trying to do this kind of work where you want to say, okay, I found a sample of objects in the outer solar system, what does this tell me about how the migration happened? It's very, very unreliable to just take the data set straight out of the Minor Planet Center. Every time you use the entire set of Minor Planet TNOs, for the love of little kittens, think about which surveys found all of these objects. So what we're trying to do with this telescope, the Canada France Hawaii telescope, and with this collaboration of scientists, which is now about nearly 50 people, it's called the Outer Solar System Origin Survey. And we're trying to provide a very large sample of objects in the outer solar system where we know where they are, we know what orbits they're on, and we know what biases went into finding them. We can give you all of the biases in a very precise way that allow people who say, here's an idea about how this structure came to be. We can statistically test it against the detected sample and see how well we can constrain the orbital structure. We do this by observing with a particularly high resolution cadence for these kinds of surveys. So rather than discovering this object, submitting it to the Minor Planet Center, and then maybe looking again at it in a couple of years, we observe the objects that we find at least twice every time that the moon is dark. So every dark time, the CFHT is pointing at our targets to try and recover them and extend the arc as these things, well, as the Earth goes around the sun and as these much more distant objects move along the tiny amounts of their arc that they move during the time we're looking. And because we're able to do this, we can end up with orbits that are exceedingly well understood. We can say if they're in resonance with Neptune or not after a tiny fraction of a percent of these things that take the better part of 1,000 years to go around the sun. So on the left here, I have orbital quality, the precision to which we know the semi-major axis of the orbits of these objects. And this is the increasing time that we've been tracking them for. So after only 2 years, we end up with better than 90% of our sample being orbitally secure to the point that we can say it is in a resonance with Neptune or it is not. This is unprecedented. This is, if you take a whole bunch of objects from the Minor Planet Center, you do not have this level of quality. So this is the power of a characterized survey where you can say, here is a sample that is very well orbitally understood. Part of the reason that we're able to get the orbits this good is that we pay an awful lot of attention to where the stars are. So an outer solar system object is moving across the sky, slowly, but it still moves across the sky several degrees in the course of a year. If you produce an astrometric catalogue, if you know where the background stars are very precisely, you can measure the movement of that moving object also very precisely. So the residuals that we have on all of the measurements of these TNOs are better than 0.1 arc seconds, which is a significant improvement on the last such major survey that was made, the Canada-France Ecliptic Plane Survey. And Stephen Gwynn at the Canadian Astronomy Data Centre is the person who's really been putting the time in to make this possible. In Star Trek, he would basically be our head of astrometrics. So at this point, we started the survey in 2013, and we run through 2016. So this is where we are in terms of discoveries. We are now, we have passed the Deep Ecliptic Survey, which ran in the mid-2000s, as the largest fully tracked sample of TNOs ever discovered. I said there were about 1,000 that you could reliably say, yes, we can point another telescope at these and find them again. Yeah, we have 440 new TNOs where we can say exactly where they are, in most cases to better than the precision of the distance from the Earth to the Moon. Something that's 40 astronomical units away, we can say where it is to within a lunar distance, or better. This is with about, let's see, that number is with 6/8 of the survey currently being processed. So we still have a quarter of the survey left to pull the discoveries out of. So we'll probably easily pass 500 discoveries of TNOs. So we're adding, an extra 50% to the number of TNOs that we can use. But more than that, we're providing the sample in a way that we know all of the biases about it. So let me walk you through this diagram. Again, there's the Plutinos just in the background in gray. But the blue dots are just general different sorts of TNOs. The orange diamonds here are the objects that we've found that are Plutinos. So this gives you some idea also of how our discoveries match the model of how Plutinos come to their closest points relative to the sun. They avoid Neptune because that's how resonance works. It's a protected region. And we're targeting regions of sky where you expect to get where these Plutinos are close. And when they're close, they're bright. And when they're bright, they're within our magnitude limit and we can detect them. And because we can detect them when they're close and bright, we can see very small objects. Because the other thing to remember about trans-Neptunian objects is they have very steep, what's known as size distributions, which is how many objects you have of each size. You have very few big ones and a very large amount of very little ones. It's like in the ocean. There are a few whales and a lot of little fish. Exactly the same thing in the outer solar system. So what I have plotted on here is currently 378 of our discoveries, and this area of sky here, which I'm currently reducing, pushes us over 400. So yeah, this is pretty spectacular. This is the kind of sample and the survey biases that come with it that you can use to really transform our understanding of how Neptune's migration happened, what was existing in the early solar system, and answer questions like, is the number of planets that we have in the solar system today the same as the number that it started with? So I'm going to take you through this in two areas where we've really been able to start placing constraints on the deep structure of the outer solar system. And yes, the first of these is the deep structure in the Kuiper belt, the highest density region of the solar system that we can see in this range. And also, I have to admit, this is a really interesting time. There's a lot of dynamical interest in what's happening in the most eccentric of these more distant objects, which our survey is not hugely sensitive to, but we can place, as I'll show you, some interesting constraints. I want to start off by only talking about a relatively small subset of our discoveries. Because the thing here is, even with a small set of discoveries, because we know all of the biases that went into making this survey, we can place very strong constraints on the structure of the underlying population that must exist. We're seeing the tip of the iceberg of this much larger population. So here is the dense core of the Kuiper belt. So 30 astronomical units in here, going out to 85. Again, eccentricity of their orbit up to the point that you see in the central Kuiper belt, and again, inclination. Things are relatively low inclination, and there's these two major resonances with Neptune, the 3-2, the Plutinos, and the more distant 2-1 resonance. The resonant objects are talked about in Kat Volk's paper, which is submitted and should be on the archive very soon. And the objects that have been dynamically scattered by Neptune are talked about in Corey Shankman's paper, which you can find on the archive there. With even a small sample like this, and you can see the blue dots here of objects that are not in resonance with Neptune, that just sit in this region of orbital parameter space, we've been able to statistically, we've been able to not reject, to use the correct terminology for it, we've been able to show that the classical belt has 3 components to it. Now, having 2 components has been talked about for a long time. You have this dynamically excited hotter population. Now, this isn't temperature I'm talking about, not thermal temperature. It's how much Neptune has thrown things around. You have a dynamically much more excited hot population, high inclinations, high eccentricities, and you have this belt of very low inclination, low eccentricity, very quiescent orbits. They just go round and round smoothly and stay very stably together. You have some self-gravitation that shuffles them around, but for the most part, they've never been disturbed by migration. And if I cast your mind back to the simulation I showed earlier, that's kind of hard to keep in these migration scenarios. You tend to dynamically kick things out and excite them, which is very consistent with the hot population, but it makes it a lot harder to conform the cold population. So that provides a really interesting constraint on how you can do this migration. Maybe you can't just do it if Neptune is the only thing in the solar system. In particular, one of the things that becomes really tricky to explain from a migration viewpoint is the substructure in the middle of the lowest inclination part of the belt, in the cold belt, which we're terming the kernel. It's very dense. It's very confined in orbital parameter space, both in semi-major axis, in eccentricity, in inclination, and also in another orbital parameter, which is the closest approach to the sun, the perihelion distance. All of these parameters confine this dense population of Kuiper belt objects. These objects have to be somehow produced by a migration scenario. Now, there's a couple of these that have been produced. Konstantin Batygin actually suggested you can do it by precessing Neptune's orbit quite fast as you migrate it with his co-authors. And more recently, David Nesvorny has suggested that you can produce this kernel as a result of when you migrate Neptune relatively smoothly, at one point you actually make it jump. And the way that you can make it jump is that you have a 5th planet in the solar system. You have another ice giant, like Uranus or Neptune, that is ejected from the system during a dynamical interaction with one of the giant planets. And as part of that dynamical ejection, you end up moving Neptune's orbit relatively abruptly. And that abrupt movement allows objects that at one time were in the 2-1 resonance, which wasn't where it is now, it was somewhere back over here, to suddenly be left behind as a little fossil population, and then the 2-1 is shoved out across to its present day location. These are very testable kinds of scenarios because they require very particular imprints of the population to exist. But because we have a characterized survey, we can say, all right, your model predicts that the population should look like this. If we apply the biases that we know that the survey had, because we measured all of them very carefully, to your prediction, that's your predicted theoretical sample of what our survey should find. Well, we just so happen to have the sample of what our survey did find. You statistically compare them, and you can either keep or reject the theoretical prediction, the theoretical model of how this is formed. So this is what you can, and yeah, you can find our discussion of how we actually confirm the existence of this kernel beyond a doubt in that paper, which is currently on the archive. There's another interesting population that exists. So this is what that same region looks like once I start putting in more of the survey, because it's an ongoing survey, so we end up with discoveries accumulating through time. You end up with that same very dense region in the middle of the classical belt. Here, the red points are showing you what's in resonance with Neptune, and how even something that looks like it's in the middle here, you need to know its orbital parameters very precisely, because that object can actually end up being in a higher order resonance with Neptune. Like here, this is a 7-to-4 resonance. It's not the kind of thing that you necessarily think of a lot, but there's a whole bunch of these higher order resonances. Most of them extend out well beyond the classical belt. But what we've been able to find with the survey is that there's actually some blue objects here which are beyond the edge of what was thought to be the terminal resonance of the Kuiper belt, the 2-to-1 resonance. This is hard to explain. These objects have been suggested before. There was one or two of them have been found actually since, I think the first one was about 2000 or so. And there's kind of been one every 5 years popped up ever since. So at the moment, about 3 were known outside of our survey, and we've found another 2. But the problem was, without finding them in a survey where you can make these kinds of statistical tests, you could just argue that one of the dynamically excited hot population objects was somehow dropped into a lower orbit here, that it was actually from a more dynamically excited population. You're just seeing one. Okay, what does that tell you? We can make this statistical test to assert that these objects that have been stirred out beyond the 2-to-1 are definitely members of the cold classical population, which implies that the cold classicals were actually extending beyond the 2-to-1 and make a diffuse disk going out further. And it has to be no further than 60 AU. We can place, again, statistical constraints that it can't extend past there. But we can also say that it has to go out to at least 50 astronomical units. And what we're implying from this is that Neptune's migration actually pushed objects out just a little further as well. It's another constraint on how Neptune had to move. So I've shown you a little bit about the kinds of detail we can get in the densest part of the Kuiper belt, where we can see a whole lot of objects, enough, that at this point you're kind of seeing much more. You're seeing so many objects now with hundreds of these in this region that we're almost starting to see the true structure of the Kuiper belt without needing to model it. It's really quite wonderful to see it come out in front of your eyes like this. But I'm going to change tack and go a little further out. Right out. Here we have, again, the solar system in top-down view. But at the top up here on the right, there's a little circle in the middle, and I think I can do this with the pointer. There we go. This little black circle up here is the orbit of Neptune. So I've been working within 10 astronomical units of Neptune's orbit in what I've been showing you just now. We're going way further out. This is the outermost part of the region influenced by Neptune. We're not in the Oort cloud. The Oort cloud starts in the 50,000 astronomical unit region. And here, I'm going out to about 1,000 or so. Beyond about 2,000 is where the tides from the other stars in the galaxy start influencing the orbits of these objects. So we're not at that regime. Instead, we're in a regime where objects could be influenced by Neptune. And some of them are. Some of them are scattering objects. They're objects with large semi-major axes, high eccentricities, and they're perturbed by Neptune on a relatively regular basis. But they intrude into this quite large semi-major axis region. But there's also even stranger objects, and I have a set of them here on this plot. These are the objects that are detached from Neptune that cannot be perturbed by Neptune in the current day solar system. They are isolated. Sedna is probably the most famous example, which you can see there with the green dashed line. their closest approach to the sun, their perihelia, is lifted so high away from Neptune's orbit that they cannot be placed there. They are fossils from some other configuration of the solar system. Now, this has got really exciting recently because we're starting to get enough of these objects discovered that discussion of them has been ongoing for the last decade. Around 2002, 2004, there were a couple of papers by Gladman and Chen going, okay, does this mean we're getting these high eccentricity, high perihelion orbits? Does this mean that we're starting to see evidence for a rogue planet in the outer solar system? Are the ones that we have now in the inner solar system, well, is there something out here? And whenever you say there is something out here, this is a statement with a long history. People have been going, is there a planet? Well, in those days it was a planet X. Is there a planet X in the outer solar system? So it's not like Gladman and Chen were the first. But then when Shepard and Trujillo found, where are we? 2012 VP113, which you can see there with the solid red line, which has, that orbit looks kind of round, at least on this projection. Then there started being talk, and they proposed in their paper that the orbit of that object would need to be formed by a giant planet in the outer solar system. Now, giant in this case is not particularly giant. We know that the outer solar system should have a bunch of dwarf planets in it. This is inherent in the way that you scatter a bunch of stuff out from the inner solar system. So there should be some Plutos and some Erises and maybe some very small on the small end of Mars-sized objects in the outer solar system. What we're talking about here is something more on what people would go planet. We're talking on the Earth mass argument. And so the question is, how many Earth masses? And if you put it there, is it going to make a signature on all of the closer in stuff in a way that would be detectable? So one of the things we can do with our survey is we can place these kinds of constraints, because you have scattering population which are dynamically interacting with Neptune and going out into the semi-major axis regime where they would be tugged on gravitationally by any such planet. And so we are able, at the moment there are a bunch of numerical simulations running which will be able to say, is the scattering population, as would be produced by a solar system with a giant planet in it, consistent with the OSIS sample? At the moment, it's not very consistent. It really, really isn't. But we're still doing one last final check before we go for publication, so I haven't put that plot up for you. What I can show you, though, is this object here in the blue, which we discovered, which is a weird one. It has a relatively high perihelion. As you can see, it's relatively comparable with the other high perihelion, high semi-major axis, high eccentricity detached objects. It goes considerably further out. If there was a giant planet of the sort proposed by Bataigan and Brown in their paper a couple months ago, it would be strongly influenced by its orbit. And the other interesting thing is proposed by Renu Malhotra and Kat Volk and co-authors in a paper that went on the archive yesterday, this is up-to-the-minute stuff, folks, is that a lot of these objects are actually would be in mean motion resonances, in the same way I've been telling you about mean motion resonances with Neptune for the inner solar, for the Kuiper belt. These kinds of objects turn out to be in mean motion resonances with proposed scenarios for a relatively several Earth mass giant planet in this part of the outer solar system. These are great. These are fascinating scenarios for how our solar system looks. And we have the data set that can provide the testing for exactly which one of these is correct, whether it's the self-gravitation that Anne-Marie Madigan suggested when she visited here a couple of weeks ago, or whether it's, as Kat and Renu are suggesting, or whether it's, as Mike and Constantine are suggesting. There's all these ways that you could produce this very strange set of orbits. At this point, I'll switch tack away from the dynamical situation that we're seeing And I'll go into a little bit of what we can tell you physically about some of these objects. Because I'm showing you plots on a graph of orbital parameters here, because these objects are points of light. They are not resolved. We have a single pixel across them. I do not make pretty astronomical pictures of lovely galaxies and nebula. But what we can say with the color of those single pixels of light is that they can tell you about the surface compositions of these small, very distant icy worlds. And we have a large program on these two facilities, predominantly on the Gemini telescope here on Mauna Kea, but also with observations from the Canada France Hawaii telescope. As you can see, they're neighbors on the summit ridge of Mauna Kea. And this program, which is another one of these big international collaborations, we have people from Queen's University Belfast, from Taiwan, from Canada, several from the US, a number from France. This is how these kinds of programs need to work. You need the expertise from a whole bunch of people around the world. The reason we're using both of these telescopes is that we're having to look at the reflectance spectrum, what these objects reflect in different wavelengths. And the normalized reflectance that you get in particular spectral bands, whether it's the ultraviolet like you see here, at the left towards your 0.3 microns, through bands known as G and R, more in the optical colors, across to the infrared J band here, near infrared, sorry. Different materials on the surface of these objects will produce different absorption bands. But on very few of these objects are you going to see a pure signature of a single material. Surfaces don't really work that way. You have a complex melange of stuff all jumbled up together. And it's going to result in deeper absorption at some wavelengths than others. And you can't just add more light and pull out a spectrum of these things. They're just, unfortunately, too faint. Well, it seems like this would be a relatively easy problem, but the problem is also small TNOs rotate, and they rotate relatively fast. So here's a perfectly typical Plutino, and it spins about every 7 or 8 hours. This is pretty typical for the kinds of objects that we're discovering with the Outer Solar System Origins survey. Because of this, if you observe it one night in one color, and then you come back the next night and observe a different color, we don't have enough information after we discover the objects to tell you which of these kinds of rotational light curves is appropriate for each object. That requires a big investment of telescope time, and it can be done, and it can be done very efficiently, but that's a completely different science question to ask. So instead what we do is simultaneous observing. While Gemini is looking in the optical and the near-infrared, Canada France Hawaii telescope, in this rather lovely picture by Joy Pollard of Gemini, is simultaneously looking at the same icy world. And that picks up the ultraviolet, and that lets us simultaneously find out which part of the same part of the surface is facing towards the telescopes, and we're able to make that measurement securely. This means that the sample that we're building, which will be about 120 plus objects when we're done, which nearly doubles, which adds again another 50% to the number of trans-Neptunian objects known with precise color information. It removes one of the major variables in trying to understand these surfaces. A lot of the times you end up with the measurements being made too far apart to be sure that it isn't just mottled surface or rotational light curve variation that's actually affecting your understanding. The reason we want to get these physical properties, though, ties back again to how these things move in the solar system. Actually, no, I do want to show you this one first. This one gives you some idea of the precision of measurements that we're able to make. So across this axis here is the optical color. So the color in green, in G band, and the color in red, in R band. And on this axis, you have the color in red and the color in J, in the near-infrared. So this is kind of your near-infrared color, and this is your optical color. And the symbols here correspond with optical properties. Correspond with orbital families. So over here where this big yellow star is, you have the solar color. That's if you just had the sunlight bouncing, traveling out to the outer solar system, bouncing straight back to you. That's exactly what it would be. And so the different colors here show you how the material of the surface modifies that solar spectrum response. Over here, this little set is the Haumea family. They're known to be covered in pure water ice. So they have a very close to solar spectrum in that sense. And you can see we have one object here, which is dynamically excited, which may very well be a Haumea family member because it's very close to being very consistent with that population. You do see a gradient in color across the range of optical colors, and you see some clustering in that dynamically excited objects tend towards the bluer end of the spectrum, and over here, objects in that population of low eccentricity, low orbital excitation tend to be much redder. This was already known. That part is not a new finding. But we can, with measurements of this precision, we're able to tease apart the interaction between color and dynamics. Color in some way corresponds to original location in the planetesimal disk, plus subsequent surface processing. It's a complex imprint that corresponds to how you form materials from an initial planetesimal disk of ice and dust and organic gooey compounds, and then coalesce it into planetesimals that we then measure in the present day. So when the sample is complete, we'll be able to make one of the, I think, the best assessments ever of how color, how physical surface property relates to dynamical composition. Because the way we're choosing this sample is that we're making a complete sample. Every single object discovered by the Outer Solar System Origin Survey, with that incredibly precise knowledge about how it was found and how that relates to the underlying population of that dynamical type, is being observed by this population if it's brighter than magnitude 23.5 in the optical band. So we're getting a really comprehensive sampling of high precision colors from all across the different dynamical populations. And this is exactly the kind of survey where you need to have a large, comprehensive, ground-based look at what's going on in these populations if you then want to send a spacecraft to it. So New Horizons, after it went past Pluto, it's still traveling. It will keep traveling without doing anything else for a very, very, very long time until it can no longer talk to us, until we can no longer hear its very, very weak voice. That won't be for the better part of 20 years yet, but in only 2019, it will get to its next little target past Pluto, which currently is rather gloriously named, well, it was named PT1, but it now has a minor planet center designation, which I think is 2014 MU69. We promise it's going to get a better name, I'm pretty sure. And so New Horizons in 2019 will be able to take pictures of the sort that it did at Pluto of one of these little worlds that I've been showing you the orbits of, and this mysterious population of this kernel of objects. The object it's going to is one of the ones from the kernel. It's not one of the ones found by the Outer Solar System Origin Survey. We don't look in the right part of the sky for that. This object sits right in the middle of the galaxy, so it was really hard to spot. You needed the Hubble Space Telescope to be able to separate out the background stars away from this object. And it will be able, from the images it'll take when it goes past this world, to tell us what's something that's about the size of Mountain View itself, what it looks like up close. And we'll be able to fit that understanding into the greater picture that we have from these kind of big ground-based surveys about the overall population, what their composition is, how that relates to the dynamical migration story. It's the difference between getting to go and kick the rock and looking at it from a very, very long way off. So both of these things are necessary for understanding how the solar system came to be in its current formation and its current configuration. but they're very complementary. So to conclude, Outer Solar System Origins Survey is now up to 400 new objects that are incredibly well known in space. Most of them, I can tell you where they are to better than the distance between the Earth and the Moon. And this is a really transformative sample for being able to tell us about how the solar system got to be the way that we see it today. We're starting to see these new populations, this density of structure within the outer solar system. And it's even starting to tell us a little bit about what might be even further out in the solar system, where the objects that we see are just the tip of the iceberg. We only see the brightest ones in the places that we happen to be looking. And the colour studies are ongoing. If you would like to see how we go with publications, there's several up here already. You can see a little more about it at osissurvey.org. Thank you very much.
We have plenty of time for questions. I'll be running around with the microphone in some approximation of order.
I'm curious what limits the magnitude that you can see. What was it, 25? Is that integration time?
I like it when people do that. So here is magnitude. So this is bright at this end, and this is going fainter at this end. Astronomers, logarithmic magnitudes, it's a pain. So 24.5 is the limit of faintness that we can see with a 4-meter telescope staring at the sky for 5 minutes straight. The reason we keep each image with the aperture, with the shutter open to only 5 minutes, while that sounds kind of short, given you go, okay, why can't we keep it open all night? We keep it to 5 minutes because we don't want the objects to move across. We're tracking at the rate the stars are moving, so we don't want the object to differentially move across that too much and smear all its light out, at which point it actually gets fainter and it becomes a pain. So our discovery efficiency, and you can see here there's different symbols for different rates of motion. Things closer to us in the solar system, so a centaur at like the distance of Saturn or so is in this lighter green 10 to 15 arc seconds per hour motion range. And we end up losing sensitivity to those slightly brighter than we would for slower moving objects because they move off the edges of the telescope field of view more quickly. So we'd lose a bit of efficiency there. This is the efficiency that we can determine of how faint we can see for different distances in the solar system, determined by putting about, this one we put about 20,000 objects into our discovery images and then recovered them again. We've actually improved that since then, and now we do about 1 million.
Hello, over here. Hey. So you had a slide that had like some things you might expect to see in the color spectrum, methane, water, things like that, with their various wavelength characteristics. And I'm wondering, basically where you got that list from, and has okay, well that's good. Yep. But has New Horizons examinations of Pluto and Charon and the smaller moons shed any light on what you might expect since 2004 on those object surface characteristics? Yeah,
this is intended to be a representative list of materials that you could have. I can make this, the USGS, this paper is a laboratory measurements of different materials of what their spectral profiles would be like across these wavelength spans. This kind of catalogue is far more extensive. You expect to have the kind of silicate minerals, so your pyroxenes, your olivines, but of course you're going to get potentially more complex other silicate minerals as well. The trick is just pyroxene and olivine tend to be ones that are more likely to be found and have good big thumbprints. So you check for those first as well. Water ice is something you do expect to find as well. You're in such a cold temperature regime around 50 Kelvin that It also depends how big the object is, whether it has enough self-gravity to hang on to some of these materials that become volatile. So methane, for example, is one we don't necessarily expect to find unless the object is relatively physically large. But you would find it on something like Pluto, which is big enough to have the gravity to hang on to that molecule. Long-chain hydrocarbon, on the other hand, is the phrase I'm using in proxy of using the word tholin, because what tholin means in different parts of the solar system is also tricky. People talk about Titan tholins or Triton tholins, the two big moons. It's very complex organic chemistry, and it's kind of amazing that you can take nitrogen ice and a bit of methane, and under the cosmic bombardment of high energy particles of cosmic rays, you end up with this goop, and it's optically quite red. But exactly what it is very hard to work out, and it can be a whole mix of different sorts of these hydrocarbons.
Hey, Michelle. I'm sure you were expecting this question from me. So you talk a lot about how you detect those TNOs. You have the orbit, the color, but you did not mention the multiplicity, the existence of multiple asteroid systems in the trans-Neptunian population.
Yep.
Do you have a follow-up program for that?
So the Gemini data is the best way that we can tell if these objects are in fact binary. So just for more context here, the binary fraction that we expect is different in different dynamical populations. So dynamical excitation tends to break apart binary structures because most of the time we don't have contact binaries. There's not a whole lot of contact binaries where the objects are physically nearly touching in the Kuiper belt, but there are quite a lot of wide binaries. And wide in this case is the semi-major axis is so large, so many, up several tens of thousands of kilometers in some case, that the orbit of the two objects is such that they're actually orbiting each other at walking pace. They're really, really slow, fragile binaries. And those are present in the cold classical population where gravitational movement of these objects has been very gentle, if at all. For our sample, the CFHT data doesn't have the resolution to find binaries unless they're very wide. So in the sample I've been showing you, we have two wide binaries, one of which was previously known. And from the Gemini data, which has a much higher pixel resolution because bigger aperture telescope, we're seeing much higher binary fractions. So we're seeing binary fractions that are entirely consistent with the HST surveys, Hubble Space Telescope, of the cold classicals. Honestly, it gets to the point that it's like, what isn't binary in the cold classicals? It's really spectacular, and it's a really interesting problem because how do you end up with a planetesimal formation mechanism if these things haven't been moved around, where you preferentially make binary systems?
So another thing that you can figure out about different populations is their size distribution. And there have been claims that different subpopulations have different size distributions. So can you say anything about that and how it correlates with dynamics or colors?
Yeah, no, that is a point that we have actually been planning to look at more now that we have the larger ensemble of data. So the size distributions that we can look at, we're predominantly focused on looking at them in the cold classicals, though I know Kat Volk's paper, yes, I think Kat did look at size distributions within the Plutinos and also I think the 5-2s in her paper. She was finding that the size distributions on the 5-2s is such that it's actually, the 5-2s are much more numerous than formation models had typically been predicting. So example, the NEAS model, which is a popular one for rearranging the solar system, does not predict the 5-2 size distribution that she found from our sample. We'll be able to, I think, so the first quarter of the survey is public. We didn't talk about size distributions in that. We'll definitely talk about the classical population size distributions. I should have that paper finished by the end of May, I think.
I have a question about resonance. And I can understand how, for example, with the moon and the Earth, that there's a one-to-one resonance. That the moon it has a bulge on the Earth's side, and that's held in place as it orbits the Earth so that we're looking at the same side of the moon all the time. But in the case of Mercury orbiting the sun, or in your cases here, you're talking about like 2-to-1 resonance, 3-to-2 resonance, and that's what I don't understand, is how the resonance, how does gravity function to lock in those resonances?
Mean motion resonances are they're an interesting problem. This is also an interesting inversion in the situation that you get, like in the asteroid belt, where mean motion resonances with Jupiter are actually more cleared of objects, where they become unstable. In the situation here, where you're exterior to Neptune, the resonance becomes a region of orbital stability to be in. So when your orbital parameters match, and they can match because Neptune is migrating, so it's actually pushing itself into the point that the object's orbital parameters are an integer value of what Neptune's are, then you end up with a point at which both of these objects are orbiting where the little minor planet is protected from further gravitational interaction with Neptune. And at that point, there can't be further scattering. Then it's safe. They just keep going around in this nice little interlocking dance. Is that?
Why does it stop there?
That,
It's slowing the orbital motion to a certain point where there's an
yeah, it's a conservation of angular momentum. So you end up actually distorting some of the other orbital parameters, like eccentricity or inclination, so that everything matches.
I kind of have just a general question. So can you comment anything on the color spectrum that you found in these outer orbital regions compared to the color spectrum maybe that the human eye can see on Earth? Have you found any, have you guys been able to maybe create a new spectrum of color that's just for these planets, and how different are they than the color spectrum that the human eye can see on Earth?
If you're looking at this with the human eye, the ones that I'm kind of in this region, your eye would see them as kind of gray. And the ones over in this region, your eye would kind of see them as maybe like aubergine, I think, is probably a good analogy. Yeah, they're relatively reddish.
You've talked about the many small Kuiper belt objects, but in a recent talk on New Horizons, they talked about the problem of finding candidate objects to visit beyond Pluto, and they said there were fewer small Kuiper belt objects than expected.
Yeah, they're probing a different regime of a different part of the size distribution than we can with this survey. So because of the flux limit that we have, we can only see some resonant populations at their closest approach to the sun. So we can only probe down to objects that are maybe the same size as Mountain View in diameter, whereas they're using Hubble Space Telescope and doing a very focused look at a very particular orbital population, and so they can see down to objects that are smaller again.
Okay, if there are more questions, please ask them, Michele, afterwards. And thank you again. And we have the toga.
Oh, thank you.